Okay, here's the third and final video in the series, and this one might be, worthwhile for everyone of the 6 math teachers to view, even those that had modern geometry, because this is the only maybe pseudo-new content to the folks that already had modern geometry, and this is modeling geometric transformations with matrices. I'm not going to look at, I also had something about additional problem solving, CXC and whatnot, but that stuff is just kind of combining all of the above. So I won't go over that in the outline I gave you, but I will cover these things in the outline. So transformations with matrices. Starting with item, 1, A1 in that outline, given an object in a transformation matrix, find the image. So here's an example problem here. Triangle PQR with these vertices, I've already graphed it, undergoes a transformation described by the matrix, and then here's your matrix right here. Find the vertices of its image, and then completely describe the transformation geometrically. All this is kind of a pretty cool application of matrix multiplication, okay? And this is kind of how it works. Here's your transformation matrix right here, -1, 0, 0, 1, which I've put here. Now I'm going to set up another matrix where I model the vertices of the triangle in columns. So notice how point P, 2, -2, I've listed it as a column here. Point Q, 4, -1, and point R, 6, -3, listed as columns. Now I'm going to multiply these two matrices together, and I know you guys know how to multiply matrices. When you're working with the Jamaican students, this is something you would need to go over much more slowly. Don't assume that they're pros at multiplying matrices, and of course multiplying matrices is kind of weird, so I'm sure you'd probably need to spend quite a bit of time just on the practice of multiplying matrices. But I trust that all of you college students know how to multiply matrices, and hence here's your answer when you perform that multiplication of this matrix and this matrix. And then the resulting columns represent the images of the 3 points. So the first column became, after the multiplication, the first column is -2, -2, and hence that's the coordinates of P prime, or that's the coordinates of the image of P. I'm going to go ahead and plot that. So -2, -2 is P prime, and let me label that. So this is P prime, that's the image. Make it bigger so we can see it. Okay, coming over here, the second column is Q prime, and it becomes -4, -1 after the transformation. So -4, -1 is here. Let me label this. This is going to be Q prime. Okay, and then finally, the last column in the resulting matrix, -6, -3. -6, -3 is over here, and that is R prime. The image of R after the transformation. Okay, so here is my resulting triangle after I make that transformation. Okay, so if I were to answer question A, I would say, okay, here's the answer to question A. Let me type it in. The vertices of PQ, P prime, Q prime, R prime. P prime is at, what is that, -2, -2. R prime is at, or Q prime, excuse me, is at -4, -1, and R prime is at -6, -3. Okay, so that would be the answer to part A in this question. And then question B is asking me to completely describe the transformation geometrically. Okay, so now I'm going to look at it visually. How do I get from this triangle to this triangle? Hopefully it's obvious to you that the triangle has been flipped over the y-axis. So this is a reflection across the y-axis. Okay, so it's just really, this is simply an application of matrix multiplication. So that's how that is done. Okay, now last thing in the outline, this should be A2. Let me change this, A2. Given an object and an image, or given a thorough description of a transformation, find the matrix that represents the transformation. Okay, so last time, you were given the matrix and you had to figure out, well, what's the transformation? Now we're going to go in reverse. You're given the transformation, and what is the matrix? So I've got 3 example problems here. Find the matrix that represents a rotation of 180 degrees with the origin as center, etc. Let me start with this. Again, this is something that you guys as college students probably have this. This is probably just crazy obvious to you. You might need to spend more time on this with high school kids. But first off, remember what the identity matrix is for multiplication. The identity 2 by 2 matrix is this particular one. Because if you multiply this particular matrix with any other matrix, it's not going to change the other matrix. It's the identity, right? So this is kind of the identity. And then in terms of, if we think about this in terms of geometric transformations, if I were to transform, if you will, a shape using this matrix, it means that the shape wouldn't really move at all. It wouldn't transform at all. This is the identity. So multiplying by this matrix would keep the shape where it is. It wouldn't move. It would stay as it was before because this is the identity matrix. Okay? I like to think of the identity matrix because I find it helpful when I want to come up with other transformation matrices, and I'll kind of explain that now. Let's go ahead and represent the identity matrix with 2 points in the plane. So let's put the point A at 1, 0, which is here. You can see it visually, and it's also here as a column in the matrix. And then B is going to be 0, 1, which is here visually. It's here in the matrix. And then what I can do is I can kind of take this baseline identity location, and if I perform a transformation with these 2 points and see where they end up is going to produce the transformation matrix that I'm looking for. So this is kind of what I mean by that. Let's start with A. Find the matrix that represents a rotation of 180 degrees with the origin as center. Okay, so I'm going to start with my 2 points A and B that are located here and here. These are my identity points, 1, 0 and 0, 1 in the matrix. I'm going to rotate each of them 180 degrees using the origin as center. If I rotate A 180 degrees about the origin, it's going to rotate over to here, right? And if I rotate B 180 degrees about the origin, it's going to rotate over, it's going to rotate over to here. Okay, so if A is rotated, it ends up here. If B is rotated, it ends up here. So the result is that A prime, the image, ends up at negative 1, 0. Write that as a column. B prime, the second column, ends up at 0, negative 1. So that's the second column. Here's your matrix that represents this particular transformation. Okay, that's it. And if you were to multiply this by any shape that you wanted to, sure enough, you would find that it would rotate that shape 180 degrees with the origin as center. Okay, let's try that again for part. Well, I'll even leave. Well, no, I want to hide it. Okay, let's look at B. Find the matrix that represents a reflection across the line y equals x. So now I'm going to reflect my points A and B across the line y equals x. Well, okay. Might be a good idea to go ahead and draw that line y equals x. Here it is. I've drawn it in red. If I were to take the original point A and reflect it across that line, it would end up over here. So A prime would be located here. If I were to reflect B across that line, B prime would end up over here. It would flip over to here. It's kind of like, it's almost like A and B are going to trade if we reflect across that line y equals x. So the result here is that after A is transformed, it ends up at 0, 1. So there you go. Okay, first column. After B is transformed, it ends up at 1, 0. Okay, so this is the answer. This is the matrix representing a reflection across the line y equals x. Finally, part C. Find the matrix that represents an enlargement of scale factor 4 with the origin as center. Okay, so if I'm going to use the origin as center and I'm going to dilate or enlarge the points A and B by a scale factor of 4, okay, what that means is, the distance from the center to A is 1, and therefore the distance from the center to A prime has to be 4 times that. So the distance from the center to A prime has to be 4 along this line, so A prime ends up over here at 4, 0. Similarly, distance from the origin to B is 1, so the distance from the origin to B prime has to be 4 times that distance, and hence it's a distance of 4 in this direction, so B prime ends up at 0, 4. Here's your matrix representing the enlargement with a scale factor of 4 with the origin as center. A couple of final notes. This neat fancy trick, it only works in cases where the center of rotation or the center of enlargement is at the origin. This trick is not going to work otherwise. And it's only going to work for, in terms of reflections, for lines that are going to pass through the origin. So the x-axis, the y-axis, y equals x, y equals negative x. But that's sufficient for the purposes of the CXC folks that you're going to be teaching. Okay, so so let's just focus on these. Always go ahead and assume when you're doing matrices that the origin will be the center of rotation or enlargement, and that the reflection lines will be kind of the straightforward y-axis, x-axis, y equals x, y equals negative x. Okay.